cough drop or a lozenge, as they say. So we're going to talk about probability distributions, and they're pretty straightforward because all it really is, I mean, it's a fancy term for a simple idea. What you're doing is you're creating a table or a graph that represents all of the possible outcomes in an experiment and the probabilities associated with each of those outcomes in the experiment. So, simple idea, if there's 1,000 possible outcomes, it could take you the rest of your life to make that probability distribution. But conceptually, it's not that bad because it's like saying, okay, well, I'll just list out all the different ways that I can get an outcome for this experiment. You know, if it's something along the lines of, you know, scores on a test or something like that out of 50 points, and only whole number values are possible. Then you can get 0, you can get a 1, you can get a 2, you can get all the way up to a 50. So you have 51 possible outcomes, including the 0. That's the easy part. Finding the probabilities of each one of those outcomes to go along with those outcomes themselves, that's the challenging piece, all right? But knowing that you need to come up with a probability to go along with each of the outcomes, that shouldn't be the problem, right? So looking at this first example, we start off fairly simply. One roll of a fair die. You think about the different ways in which you could have an outcome for one roll of a fair die. Well, you can get a 1, you can get a 2, a 3, a 4, a 5, or a 6. All those outcomes are equally likely, which means that you have a 1 in 6 chance of getting a 1. You have a 1 in 6 chance of getting a 2, a 3, a 4, a 5, a 6. All right. So what we have here, what I just created, those two columns, that is your probability distribution. The rest of the table is us using that information to draw conclusions. I just dropped something expensive. Hold on. I think it's all right. My charging station is nothing short of a fire hazard. No, here's what it is. So anyway, probably shouldn't have said that in a recording going out on the internet. All right, well, I will be unplugging one of the 17 things that are plugged into this outlet forthwith. Okay, anyway, so how do we verify that a distribution is a probability distribution? Well, one way, and the best way, is to take the sum of all the probabilities. Right? So that means just add them all up. So just take a quick sum. If you get a result of 1, that means that you've accounted for 100% of the possible outcomes. So we have a common denominator. This amounts to 6 out of 6, which is 1, which is the same as 100%. All right. If you've accounted for 100% of all the outcomes, you have all of the outcomes. Right? And since the criteria behind a probability distribution is that you've accounted for every single possible outcome and all the probabilities that go along with them, then we've accomplished our mission here. All right, so at the bottom there it says note, P of X is between 0 and 1. All that's saying is that probabilities have to be between 0 and 1. Right? 0 being impossible, 1 meaning that it's certain. But also the sum right? That funky E looking thing is a sum. The sum of the P column has to be equal to 1. Otherwise, it's not a probability distribution. Right? And a lot of the stuff that we do based on that information would be invalid. Right? So what we can do is we can do a couple of things. We can find the mean of a probability distribution, and we could also find the standard deviation of a probability distribution. Right? None of which is overly complicated. For a small data set, not too bad. Not too bad at all. But for a larger data set, it could be prohibitive. Let's move this here. So if I want to find the mean, you can see this good looking formula down. Let me get a color here. This good looking formula down right here. Let me get a more rectangular looking rectangle around that. That's a formula that'll help us find the mean, but all that amounts to is taking the sum of the column x times p of x. So I'm going to multiply across 1 times 1/6, 1/6, 2 times 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6. All right. Mu, right? So that m, that letter M U hybrid is the Greek letter mu. Right? So it's, think of it as like M U, mu. All right. That stands for population mean. All right. Since we have 100% of all possible outcomes, that makes it a population. All right. So again, it's the sum of all the x values multiplied by the p of x values. I'm just writing it in a little more shorthand notation, but that's essentially what it is. All right. So what I'm going to do is I'm just going to add up this column, the one I highlighted in green. All right. So that's going to be equal to, I can do it in a calculator, but really it's just a matter of adding up the numerators. 11, 15, 18, 21. So 21/6, which is equal to 3.5. All right, so my population mean is equal to 3.5. I mean, it's not an overly meaningful outcome from an ordinary perspective, because you look at it and say, well, how do you get a 3.5 when you roll a die? You know, they're discrete. You can only get 1, 2, 3, 4, 5, or 6. What this is saying is if I rolled the die 100,000 times and averaged the value of the size that I got. So sometimes I got a 2, sometimes I got a 4, sometimes I got a 1, sometimes I got a 6. Add them all up and divide by the number of dice that I got, that I rolled, then it would amount to a 3.5. Right? So what this is also known as the expected value. Standard deviation involves a little bit more work, but nothing too crazy. Right? So the formula makes it look like it's crazy, but it's really not too crazy, because you do have the support of a calculator. Right? So you do have to run through the remaining columns. So x squared, and I'll do my little highlighting action here. Let's see, this is a fun color here. Got a nice little orange there. Yep. Better. So, oh. All right, I'm gonna live with that. I'm not gonna argue with it. to x sub I squared, which is really just saying x squared. The little subscript of I is really just talking about the position within the sequence. So if I said x sub 2, that means the second value in the x column. So really, most people just kind of do without the little I, and that's perfectly all right. But what I'm going to do is I'm going to square each of those x values. So 1, 4, 9, 16, 25, 36. Then I multiply those values by p of x sub I. So the p column. So we're going to take these two columns, this one and this one, and multiply. So I'm going to get 1 6. I'm going to get 4 6, 9 6, 16 6, 25 6, and 36 6. Now the inclination might be to try to reduce, like 36 over 6, you want to write 6. But we have a common denominator, so it's kind of in our best interest to resist that urge. So what we'll get here, what we're looking for anyway, is the sum, poor quality sigma symbol, of x squared times p of x. Using the same idea, I'm going to add 61, 77, 86, 91, I think. Actually, those circles got a little out of hand. I'll just write 91 over 6. 5, 14, 30, 55, 85, 91, right? 91 over 6. Now you can divide if you want. Put it in fraction form, that's up to you. But there's really no need to, because we're not done with the problem. Right? As you can see, hopefully, in the formula here, that I have my summation. That's what I just figured out here. I'll just kind of highlight that. This guy is this one. So that part's okay, but I do have to subtract from that the mean squared. Right? So my standard deviation would be equal to, I'm going to create a radical here, 91 over 6 minus 3.5 squared. I'm going to let the calculator do that for me. And you get about 1.708, approximately. Okay. Now, that Greek letter, that's, hey, well, that happened quickly. Sorry, giant scheme. I don't even know why I have it on. It's like you blink and they're already down the field. So this is a lowercase sigma. And it stands for population standard deviation. All right, so it's a measure of spread, but what it's telling us is that we can do all the stuff that we did before with populations, you know, like usual and unusual values. We can create normal curves. We can evaluate normal curves, all that good stuff. All right. So more on that later, but there is a method to it all. All right. And so once we get there, you'll see it'll make a little bit more sense. Now, the biggest question I usually get after this whole spiel here is, wait, are we gonna have to do this? Of course not. I'm not gonna ask you to do any of this by hand. You do it on a calculator. I gotta show you how to do it on a calculator. I gotta show you which calculator, which resource is the best option to use, but definitely technology is the way to go here. All right, so I'll show you a few different options. Well, a couple of different options. All right. I think the preferred way that people have come across in the past ends up being a more kind of a spreadsheet approach, but I'll leave it up to you. All right. So yeah, we're going to talk about larger data sets, but before we do that, I just wanted to draw your attention to these two terms here: discrete random variable and continuous random variables. Random variables that are made up of countable values, and random variables that are not made up of countable values. Countable as in, like, you can point to them and determine their value. So I got 5 chairs in a room. I got 7 light bulbs. I got whatever, you know, like something that I could physically count up. How many students are in my class? But when you get into heights, weights, lengths of time, and things like that, that's when you need some kind of measuring device. And that's for continuous data sets. Some of the distributions that we deal with only work for continuous data sets. And so what we need to do is we need to kind of merge the two ideas. How do we get from one to the other? How do we get from a discrete data set to a continuous and vice versa? Right. I'm going to toss the example on the bottom. I'm not going to ask you to do anything related to that. So, and we'll hop on over to the next page where you have a mega not graph, it will be a graph, but a mega distribution. All right, and I have at the top here that mu plus or minus 2 sigma gives you the usual range. All right, unusual values fall outside of that interval. So the example, gender core claims its gender selection technique will statistically significantly increase the likelihood that a baby will be a girl. A study was conducted to verify this claim. During this study, 14 expecting mothers followed the patent pending program purported by Gender Corp. Each of the 14 mothers had successful full-term pregnancies yielding 11 girls and 1 boy. All right. I think I meant to edit that at some point. That just makes it seem like each one of them had 12 kids. That's not the intent. And also, those two numbers don't add up to those two numbers don't add up to 14. So, yeah, need a little rephrasing of that bad boy. There should be a 3, and the 14. So not each. The yielding a total of 11 girls and 13 boys. All right, so that's a typo opportunity for somebody. Because otherwise, I mean, I could already imagine people cringing over that one. Like 12 kids. So, yeah, that's, I don't know what else to say. It's Monday. I don't have an excuse though, because I typed this up like 3 months ago, whatever. Or at least I edited it 3 months ago. I typed this packet up like 20 years ago. I've been just editing it over time. Yeah, so the intent was that you had 14 mothers, so each one of them having 1 child. You know, we know that that's not always how it plays out, but that's what we're assuming here. There are 14 full-term pregnancies, giving a result of 11 girls and 3 boys. You know, unfortunately, it is possible to have less than, you have 14 pregnancies and less live births, but that intent of the question was not to be disturbing and morbid. Right? The following distribution represents the probabilities associated with the number of girls yielding from 14 live births, with the assumption that for each pregnancy, there's a 50% chance the child is a girl. So a lot of assumptions going on here. The one big one is that it's a 50-50 split between those two genders. Okay. So the first thing we would do is graph the distribution. Honestly, I got to say, I really don't have it in me right now to create a graph by hand. So what we'll do is we'll use technology from beginning to end on this, but it is going to involve us having to type in the data. All right. So we're going to go over to Google Sheets, and I'll show you how to do this. because this ends up being a nice little reference for you. Because when you come across a problem like this on a test, there's no reason why you can't just model your work based off of what we do here. Right? So that's my thinking anyway. And I really wish I had the foresight to type this in, or at least save the original table from my Word document, but I didn't, so here we are. All right, I'm also going to do it on my laptop screen, so I'm going to jump out of the iPad share and open up Google Sheets and just kind of walk you through it. Just cleaning up a little bit. All right, so some stuff in the way here. I want sheets. I'm going to create a new one, a blank one. And I'm going to type in these values. Overshot the mark. A few of that's. Got a little stray mark there. I don't know why, but I do. .000 is really just trying to say 0. So you could just type in the 0. 001. .006. .022. .061. .122. .183. .21. .183.
The probability of there being either all girls or no girls.
Say that again?
This is the probability of there being either all of one gender or none of a gender.
From all of one gender to none of one gender, yeah.
Yeah, it's like a sliding scale, essentially.
Yeah, exactly.
Cool, thank you.
No problem. All right. So I got my data in. Now there's a couple of ways that you can handle it. One way would be to pretty much do what we did, which is to say, like, multiply the x by the p of x and then total it out. You know, you could do it that way. There's nothing wrong with that, but there are built-in functions that'll compute statistical values for you. So if I wanted to, and I do, type an equal sign, and you see the different options that come up as suggestions based off of what you see. But if we want to find the mean or the average, we have different types of averages. You know, you have the average of a simple raw set of values, average based on conditionals, and then you have a weighted average. All right, so weighted averages can be a little on the trickier side, but it'll spit out the value that'll give you, it'll tell you what the expected value is for a particular data set. All right. So I'll walk you through that, but it's really just weighting each of the X values based off of their corresponding probabilities. So this is giving us what it thinks is the probability of getting a female birth. But that's the thing, like our common sense tells us it's otherwise, you know, so that's, you got to be careful about that. So I'll take you through the table approach. So X multiplied by P of X. I'll just use a little star symbol to represent the multiplication, but X times P of X. That's really just taking the first entry in the first row and multiplying it by the first entry in the second row. And then when you hit enter, you get that product. And then you can just drag it on down the line. I think in the end, instead of looking for different functions in Google Sheets or Excel, this ends up being the better way, because we have the formulas, we had them on the previous page. It's really just a matter of manufacturing a spreadsheet to make this all play out that way. So then what I would do is I would type in mean, put a little colon here, maybe make it bold. And, you know, take the time to make it look nice for your own benefit. That's up to you, because what happens is people don't take the time to make it look relatively nice. I aligned it to the right, and they go to try to use it on a test or something like that, and they end up paying a price. Right? What we need to do here is take the sum.
Like what you did to me.
Like what I did to you. Right, so the sum of C2 to C16. Now it says, oh, I didn't type in sum. Kind of important that you tell it what it is that you want it to do with the information in the column. And you get the sum. The mean should have been 7, because really, if you think about it, there's a 50-50 chance, boy or girl, then there's 14 births. And probability says that it should be half one way, half the other, right? But it doesn't always play out that way in the real world, but you know, that's what the math says, right? So multiply across. So we take the A2 and multiply it by the B2. That gives us this cell. Slide it on down the line, or copy paste it on down the line. And then this entry should just be the sum of all the entries in C2 to C6. So all of these added up should give you a 7. Right? Different from the weighted average, but you know, they both could have meaning. It's just this is the mean of a probability distribution. The other one isn't, although it sometimes feels like it is. All right. Then what we would need to do is find the column that gives us, you can do a combo here. You don't have to do it in 2 separate columns. You could do it all in one shot. So what I would recommend is you do that, because Excel and Google Sheets can handle it. So we're doing X squared multiplied by P of X. So this, that little caret symbol means squared multiplied by P of X. The column headings, you can write those any way you want. I just chose to write it in symbolic form, but you could actually just write out X squared, S-Q-U-A-R-E-D, times, T-I-M-E-S, P of X. You know, like you can just like write little notes to yourself, right? But what I'm doing here is I'm taking each of these values in A, squaring it, and multiplying it by P of X. All right, so just do that the one time and then drag it on down the line and you'll have it. So A2 squared multiplied by B2. And it still ought to be 0. You know, like you can type it in wrong and still get a 0. So that's dangerous, but it isn't until you drag it on down the line that you realize, oh, okay, I think I might have done it right. You get this array of values here. And so what we want is the sum of all of these, right? So it's just a question of where you want to put that, because sometimes it could get a little messy. You know, again, a little bit of formatting goes a long way. So you know what your mean's going to be. And kind of shrink that down a little bit. And then maybe off on the side here, somewhere in this area, you can do the sums, but really it's the idea that you want to take the sum of that under a radical and subtract off the mean squared, right? So you can put that anywhere you want. Maybe you put it underneath, you know, so maybe you say standard deviation. And then just pop it right below. It's up to you. Use the format painter and get the boldness and the highlighting just so you have your answer where you want it. But in here, what I'm going to type is equals. I want the whole thing to be eventually under a radical. Okay? So it's the sum of all the entries in this column. So I can drag, or I can just type in D2 colon D16. All right, that entry is going to be squared. Oh, I'm sorry, minus that entry, subtract from that entry the mean squared. Put the emphasis on the wrong swallow there. So minus the mean, which is this guy, squared. All right. Now, the one thing you got to be careful about is if you go to copy and paste this based off of row references and things like that, you may have to throw some dollar signs in here, but this is all we're using this for. So that should be fine. And when I hit enter, it gives me the standard deviation. Okay. So it's a mean of 7-ish. Oh, well, 7, sorry, a standard deviation of 3.5-ish. All right. So we got everything we needed just by typing it in here. Now, the benefit of using this kind of approach is if I wanted to change my data, since everything here is calling back to what's going on in C2 to C16, and everything in here is calling back to prior computations, I could change all these values here, you know, just wipe it all out and put in a different set. You know, it's kind of heartbreaking when you do that. You type in all that stuff just to delete it, but and so you see the values here are off, but that's because I have all these extra zeros. Just wipe those out, and then we should end up with a couple of adjustments. It's not C2 to C16 anymore. It's C2 to C7. There's ways to kind of tweak this, but you can just kind of do it on the fly here. And you just look and say, well, I don't need it to go all the way down there. It highlights it for me. Say, oh, well, I'll just stop this one at 7. And so we get some values that way, although something went a little haywire here. I don't know why it's not.
Does your standard deviation, the first part of the equation there, still say 17, or did it adjust automatically?
Oh, thank you. Oh, wait, no, 17. C17.
Is this correct? Because isn't it 2 times 1/6? Shouldn't that go to 2/6 or 1/3 instead of 1/13?
Yeah, that's what I'm looking at. I'm like, why did that happen?
And the rightmost column is also, I think, too small because it's squaring x. So
Yeah, there's something. Ugh, I don't like that. Let me undo. I just don't want to lose the stuff that I had before. That was really strange. What? 8? It was saying A2. It could have been a formatting thing. All right, well, I don't want to get too ambitious, but I think it's because I put in 1/6, 1 divided by 6, and the formatting probably has that set up to be something else, like the date. like it thinks I typed in January 6th, right? That's my suspicion. So I'm just going to leave it like this so that I don't run the risk of causing more problems. Right. So this is one way that you can do it. Right. There's other ways, but you know, it's this goes along the lines of everything that I've been talking about, where it's like, hey, you like a method and it works, then go for it. But keep an open mind to other techniques, right? Because we can do this on Desmos, we can do it on GeoGebra, right? But I know people are kind of anti-GeoGebra, so I know that's kind of the last thing that you want to hear out of me at this point. But this is really enough for us to get started on the problem, because we needed the mean. I'm writing it down before I change my display. Mean of 7 and sigma of approximately 3.516. I think my Apple Pencil's dying. All right, so let me go back to the other screen. Bring it up. All right, so this is the mean and the standard deviation. But if you wanted to, you could have created a table in Desmos. It's more typing, you know, it's not something that most people want to get into just, you know, at this moment. But I'll show you, like I said, I'll show you another way. But for now, we'll work with these numbers. We need mu plus or minus 2 sigma. So that's the same as saying 7 plus or minus 3.516. So 7 minus 2 times 3.516, 3.516. So on the low bound, we're going to get negative 0.032. And then we can do the same thing, just making the minus into a plus. So 14.032. All right, so that gives you the interval of usual values. All right, so what it's saying here is that it's not unusual to get values in between negative 0.032 and 14.032. The issue is I must have screwed something up, and I'm kind of like exhausted right now. So my patience with myself is very limited. Back to the Google Sheets, because I've been doing the same problem for like 20 years. There's always some unusual value. So let me just bring it up. Yeah, forgot the radical. So it's got to be raised to the 1/2 power. So with a little carried 0.5, it should have been 1.875. So apologies for that. Like stifling a yawn every 2 seconds also. It's not helping anyone. I'll try to do it off camera. Whew. All right, so anyway, yeah, I missed the radical there, which is part of the formula. But like I said, I'll be showing you a different way in a little bit anyway. So it's up to you. All right, so I'm going to use a technique that I like to call the right way to answer this problem. So 1.876, 1.875. I'm just writing it down on my little tablet here before I change the display again. All right. So,
Professor,
yeah.
Sorry to bother you. I know you're tired. Are we gonna do some reviews tonight or no?
We got to get through this stuff first, but
Oh.
yeah, we'll do some review.
Okay.
Here. Oh boy. All right. 1.875 is getting added to and from, subtracted from. So on the high side, I'll get to the low side in a sec. We're looking at 10.752. Then on the low side, 3.248. Right. So when you mark up the diagram, you're looking for any value that's bigger than 3.248, but smaller than 10.751. So that would be this set of values here. So these are the usuals. All right. Anything that falls outside of that interval is going to be considered unusual. All right. So 11 definitely falls outside of that interval, but not by a whole heck of a lot, but it does fall outside of that interval. So therefore, the three dots in the form of a triangle means therefore 11 girls in 14 births would be unusual. Unusual on the high side, but what that's telling us is that if we left it to chance alone, you know, you let the fates decide, it would be unusual to get 11 girls and 14 births. You should, the closer you get to 7, the more likely you are to, you know, have a strong probability. You know, so like if I were taking a guess, they said, okay, there's 14 children were born last night in the local hospital. Right? How many do you think were boys and how many do you think were girls? Like if you guess around 7 either way, you're playing it safe. You know, if I said 6 boys and 8 girls, right? Nobody's going to look at that and say, all right, well that's absurd, all right? But if you were to say they were all girls, somebody would say, well, if we're putting money down on this, say, well, that's probably not a smart bet. 14 births, you think every single one of them were girls? And I'm not talking about getting the Chinese calendar involved here. You know, it's just straight up based on the numbers. You think out of 14 births that all of them were girls. All right, I'll take your money. You know, same thing the other way. All of them were boys? Nah, you got to hedge your bet somewhere. 4 and 10, okay. You know, I'll go with that. Maybe it's girl season. You know, so that seems to be the case. It's like it's completely anecdotal, but I'm sure we've all kind of had that eyebrow raising moment where, you know, a bunch of friends are pregnant and they're all having kids and it's like, whoa, another girl, another girl, another girl. And then like 2 years later, it's like, oh, all boys. Everybody's having boys now. Oh, what's going on here? You know, so it's possible that you could have a run on one particular gender as opposed to another, but odds are it's going to be some kind of split. Just a question of what that split's going to be. Right? So here we're saying that it's pretty unusual to get 11 girls and 14 births. So if this company can actually make that happen, you know, if they give you a you know, some sort of program to follow that's going to lead to that outcome, then considering that it's unusual that it would happen based on nature, if it does actually happen, then we could say, or we can conclude that there must be some sort of effect that this company's program must be having some sort of effect on the situation. Right? That's all this concept is really trying to get across. Right? Yeah. So other methods for handling this, because I know the Google Sheets isn't always the most user-friendly way of handling this. there is GeoGebra, but you could also, nothing wrong with using an online calculator, so some computational aid that'll compute, determine these values for you. Right? In a little bit, I'll take you through some options for that. Right? But for now, I wanted to hop over to something called the binomial probability distribution.
Did we
Right.
say what kind of distribution that last one was? Did we answer that
What?
question?
Say it again.
For the last question, did we answer the graph this distribution? It's not a uniform distribution. Did we say what kind of distribution it was?
Oh, it turns out it's a normal distribution, but I kind of skipped over that part.
Got it.
But yeah, for the good of the order, it is in fact a normal distribution. And that would be because the bulk of the data lies towards the center, and it gets less and less likely as you work your way out towards the fringes. Now, a binomial distribution is a special type of probability distribution, right? So it follows these four conditions though. And the conditions are that there's a fixed number of trials. I'll get to what that means in a minute. A fixed probability, independent events, and two outcomes, right? The easiest thing to remember is the two outcomes part, because that's the bi part of binomial. Right, so the fixed number of trials is telling us that the number of, well, to use the word in its own definition, number of trials in a situation is not going to be dependent on anything in the experiment, right? So it's not a choose your own adventure situation. So if you were to say, for example, you're playing a game, and if you roll the dice and you get doubles, you get another turn, right? That would be a case where something that you did in the game impacted the number of trials that you have, because everybody else would get one turn, you get one roll of the die, but you get two rolls of the dice because you got doubles, right? So that would be a case where it's not a fixed number of trials. We're only going to be working with the cases where it is a fixed number of trials, like number of questions on a test. You don't, if there are 10 questions on a test, depending on how you answer those questions will not impact how many more questions you get. Unless it's something like IXL, if you've ever done that, where it's like, oh, you got one wrong. Well, guess what? Now you got to answer like 15 more questions. This isn't that kind of situation. Right? Fixed probability is not going to change from trial to trial. So, you think of a multiple choice test, for example. If I get the first question right, the 1 in 4 chance of getting the first question right, that's not going to impact the probability of getting the second question right, or at least in this situation. You got to assume that they're independent questions. Each question is going to be their own self-contained concept. Right? It is possible that there could be some overlap of concepts, like, well, if you got number 1 wrong and it's similar to number 2, and you're probably going to get that one wrong. This isn't that, right? And also, when you answer questions, so you see this pop quiz here, you're not answering it based off any prior knowledge. You're answering it based off of random selection, right? And that's where the independent events come into play, because, if I'm going to make a random selection, I'm going to do it, and I'm going to be truly random about it, and I'm not going to take into account any previous outcomes. So looking at this pop quiz here, and there's a reason why there's no questions, just the choices. The whole idea is to be completely random about it. So let's say I let the first one be B, the second one I want to be B, third one I'll do B again, and C, and let's do D again. All right. The minute you put any thought into it, it's not random anymore. So, it's kind of tricky, because in that last one, I was like, well, I haven't used A yet, so let me pop in an A there. But then I was like, oh, that's exactly what they would expect me to do. So I'm not going to choose A. So it all kind of varies. But then the question that follows, bubble in an answer for each question on the pop quiz, and then state the number correct. Well, you wouldn't know that until I gave you the answer key, which is B, C, B, A, D. All right, so these are the answers. All right, so I got this one right. Second one I got wrong. This one I got right. Third one I got wrong. Fourth one I got wrong. And the last one I got right. So actually not too bad. Not too shabby. I got 3 out of 5 right just by guessing. I didn't even know what the answers were going to be going into it. You know, completely random. And you know, as random as it can be. You know, I made up the choices and then I made up the answer key. So it's possible that you know, there was some subconscious work going on there, but that's the idea, is that there's completely a random outcome involved. So I got 3 right. All right, so how many did you get right? I got 3. Let X represent the number of correct guesses. Is this a binomial setting? Explain. Well, the binomial setting has to do with the 4 conditions. So I'm asking myself, was there a fixed number of trials? I didn't do the right thing there. I need to do a screenshot. Then I copy. And I paste. Learning curve. Oh, why did that jump on me? Lord only knows. All right. So was there a fixed number of trials? Yeah, there was 5 questions. That didn't change throughout the process. All right. Fixed probability. Yeah, I got a 1 in 5, 1 in 4 chance every step of the way. All right. None of the choices disappeared along the way. If I chose choice A for question 1, that doesn't mean I can't choose question A for question 2. Choice A for question 2, 3, 4, 5. So that's fine. And then success or failure. I mean, that is the definition of success or failure. It's right or wrong. All right. So this is going to be a yes. And because all 4 of those conditions were satisfied. If any one of those conditions were not satisfied, then it would not be a binomial distribution. So then they say, calculate the probability of getting exactly 2 right and show your work. Right? That's the trickiest part of this whole thing. Right? So I'm going to walk you through that, and then I'll show you a couple of shortcuts that'll help you along the way here. All right? So probability of getting exactly 2 right. Right? Because we're letting X represent the number of correct guesses, we would say X is equal to 2. Right? So we have to kind of think this through. It's possible, because there were 5 questions, right? It's possible that I can get 2 questions right in a variety of different ways. All right. So I could be looking at, maybe I got the first 2 questions right. So I'll say correct, correct. And then the remaining questions were incorrect. All right. Maybe I got the second and third questions right. So correct, C for correct, I for incorrect. Maybe it was the third and fourth questions that I got correct, but everything else incorrect. Or maybe started off slow, but then came on strong. That's assuming that the questions that I got correct were consecutive. And maybe they alternated. Maybe it was correct, incorrect, correct, incorrect. And then it finished with a little fizzle there and got one correct, incorrect. Right? Maybe I started off incorrect and I got one correct. And I got another one incorrect. And then another one correct. And then finally ended up with an incorrect one. That's a possibility.
So it has to be 2 correct?
Yeah.
Yeah, binomial?
Yeah. Well, no, not 2 correct to make it binomial. 2 correct because that's what the question's asking.
Oh, okay, yeah.
All right, we still have a few more possibilities here. Maybe the first and last one were correct and the ones in the middle were incorrect. All right, maybe it was the first one that was correct and then I got a couple wrong. And I got one correct. And then I finished up with an incorrect one. All right, so that's a couple more there. So now I just got to figure out what the last two were, because that's always where I end up. Yeah, let's see. It could be the first, and now I got the first and the fourth, first and the fifth. It should be 10. That's what I'm getting at. Incorrect, correct, correct, incorrect, incorrect. I got that. Incorrect, correct, incorrect.
Let's take the second row of the right and then move that whole thing to the right. Move the two correct, so it's rightmost and centermost.
So,
Yes.
okay. And then there should be one more. Oh, I see. It's like going backwards. It's like taking that first row and reading it backwards. Maybe there's something to that.
Second row from bottom on right, shift that to the right.
All right. Well, there's 10 of them there. They all look unique. And it's very easy to lose your mind with all this stuff. But I just wanted to make sure that we got a little bit of a sense of just how involved this stuff is, because yeah, there's a formula. It's written above. That formula, people look at it and say, well, I don't want to work with that formula. That thing's crazy. But then you look at this and you say, well, I got to figure out each of these probabilities, because we haven't even tackled the probability yet. But fortunately, each one of these is made up of 2 corrects and 3 incorrects. Right? So let's just look at one of the cases. I would say the probability of getting a correct answer on any one question, 1 out of 5. The probability of getting another one correct would be 1 out of 5. Then the probability of getting incorrect would be 4 out of 5, 3 times. All right, so all I'm doing here is evaluating that first case, knowing that the remaining cases afterwards are going to be identical, right, in terms of value, because this amounts to 1/5 to the second power and 4/5 to the third power, right? And no matter which case you take, if you wanted to, you can go look at the 8th case, for example. You see that we still have 2 corrects and 3 incorrects. It's going to amount to the same stuff. So what that's telling me is that if I know how many ways you could have 2 correct and 3 incorrect, which in this case, it turns out is 10. Now, there's a reason why I knew to look for 10 going into the problem. I got to get to that in a sec. But if I know that the total number of values in the set would be 10, total number of arrangements in the set would be 10, then I could just multiply this quantity by 10 and get my answer, right? So the theme of all of this, everything that we're covering tonight is there's got to be a shortcut. And we're getting there. So you multiply it all out, whether you're using an ordinary calculator or a Desmos, you'll get the result, which would be 0.2048. So you got a 20% chance, 21% chance of getting exactly 2 questions right on a test consisting of 5 questions if you were to just guess. I mean, it feels like an answer that could be all right. It could make sense. But then again, it also feels like something like, how would I know? How would I know that makes sense? But I do have an entry that I could put in the table. Now I just need all the other values in the table. And you look at it and say, whoa. It took us forever to come up with this. How are we going to do it for the remaining values here? That goes back to what I was saying before. There's got to be an easier way, right? So there's the formula there. Nx, ncx, p to the x, q to the n minus x. You look at that above. I'll mark it up here. This stuff here, which actually would get you to this a lot quicker, because the n represents the number of trials, right? So this would be 5 trials, 5 questions, C2, that's the number that I want to get correct. Probability, P is the probability of success. I got a 1 in 5 chance of being successful on any one trial, so to the 2nd power. Q is the probability of failure, and that would be to the n minus x. So here's n, here's x, 5 minus 2 power. All right, so 5C2, pop it in your calculator, gives you a result of 10. Everything else just kind of works itself out, right? It all ends up being the same stuff that we have here. So you could do it that way, but if you go into functions under distributions, you'll see that there's a function for binomial distribution. Okay? So if you type in trials, 5 trials, success probability, right? So success probability is 1 in 5. All right, that would be the distribution itself. But you see here, there's an option to find cumulative probabilities. It asks you on an interval, what is it that you're looking for? All right, so if you set the min and max to the x value that you're interested in, it'll just spit back the numbers for you. All right, so 2048 is what you're looking for 2 trials. That's the probability. All right, now you could also grab an interval out of this. If I needed to find the probability going from 0 to 5, for example, I can do that. What's the probability of getting anywhere between 0 questions right and all of them right? Well, it should be 1. There's a 100% chance I'm going to get somewhere between none of them right and all of them right. All right, so that's interesting. But I can do just 0 to 0. That's 0.32768. I can do 1 to 1, 4096. 3 to 3. That's the one quirk in this, where it's like if you want just a specific value, you typically just put in the min and max. You know, there's other ways of handling it, but this is the way that confuses people the least, if you can believe that. So 0.0512, 4 to 4, 0.0064, and then 5 to 5. And you could see, hopefully, when you look at this, that the probability gets less and less favorable as the x value gets larger and larger. And that should make sense, right? And that's because, well, I'm guessing on a test. There's 5 questions on the test. If there was a chance that if there was a good chance that I could get them all right just by guessing, why the hell would I study? All right, and then I would expand that to a 100-question test. I'm thinking right back to like psychology 101 in college. Like those were all multiple choice tests, like 50 questions. I wouldn't have to study at all. This is great. As it turned out, I didn't study it all anyway. It did not play out in a way that was favorable, but you know, sometimes you get, you know, broken watch is right twice a day. So we could find the mean of this distribution by hand, but I've bored you enough. I'm going to give you the shortcut for the mean of a probability distribution. Mean, and it's detailed on the next page, but I'm just going to write it here. I'm sorry, of a binomial distribution. That's mu is equal to n times p. Actually, one of the shockingly easier things to determine in this course. Most of the time, it's like some convoluted formula or process on a calculator. This actually isn't that bad because n is the number of trials, and p is the probability of success. So it's still the same n and p from above, but that's off screen right now, so I figured I'd just write it. So 5 questions, 1 in 5 chance of getting a question right. 5 times 1/5 is 1. Again, the mean of a probability distribution is also known as the expected value. And that's really the interpretation. So it's how many questions would you expect to get right on a 5-question test if there were 4 choices and I'm sorry, if there are 5 choices. Oh, dang it. There were four choices, weren't there? Son of a gun heck. Well, guess what? There are 5 choices now because I just can't do this. There we go. On a 5-choice, 5-question, multiple choice test, right? My expected value, my expected number of correct answers would be 1, which is kind of in line of what you would expect. If you're just going to guess on a test, you don't expect to get a whole heck of a lot of them right. Right? Now, the variation, the standard deviation, measure of variation, that formula, so standard deviation of a binomial distribution is sigma equals the square root of NPQ. All right. So N is the number of trials, P is the probability of success, Q is the probability of failure. So in this case, I'm taking my sigma, or I'm sorry, I'm taking my N, I'm multiplying it by 1/5 for the P. That's the probability of getting something right, and 4/5 for the Q. That's the probability of getting a question wrong. So 5 times 1/5 times 4/5 is going to be the square root of 4/5, which we can just crank out in the calculator. About 0.894. And so that's the measure of variation. All right, so we have the expected value and the measure of variation. It's the spread, how spread out the data is, or so we're not looking at a data set that's very much spread out. We're saying that the bulk of the data is roughly within 1 unit of 1. So you can reasonably expect to have anywhere between 0 and 2 values correct by guessing out of 5, which is not going to get you into the passing range. All right, but most people don't go into a test thinking, well, there's a good chance I'm going to get a 100 on this just by guessing. So that's why you study, but the probabilities back that up too. So I kind of stole my own thunder on the mean and standard deviation in the area below. See here, that formula, sigma is equal to the square root of n p and then 1 minus p. That's the same as q. Okay, so it's the same thing. Now 7 and 8 is saying what's the probability of getting at most 3 correct or at 3 or more correct. There's no difference in the approach from what we're doing here to what we did previously. At most 3 correct is the probability that x is less than or equal to 3. Right, so I would do my binomial distribution. Still the 5, 1/5. But then for the min, well, the fewest questions I can get wrong would be 0. I can get it back. I'm sorry, get right would be 0. I can get them all wrong. The most I can get right would be, in this circumstance, would be 3. So I'm just going from 0 to 3. So we would be looking at a probability of approximately 0.993. All right, at most 3%, at most 3 questions correct out of 5. 3 out of 5 is 60%. All right, so 60% is like borderline failing passing. So we're saying that there's over a 99% chance that you're probably going to fail if you just guess. All right, still consistent with what you would expect. All right, now 3 or more correct, that's going the other way. I can still do a little copy pasting here. So if x is going to be greater than or equal to 3, well, there is a cap to how far you can go. You can't get more questions right than there are. Right? There's only 5 questions. So my maximum would be 5. So I would min it out at 3 and I would max it out at 5. And so we'd be looking at 0.0579. All right. So that's really all you'd have to do, because the calculator is doing all the work for you. It's really just a matter of knowing what to put into the calculator. Once you figure that out, it's a whole lot easier. Right. So then the last thing that we'll do is number 10, because number 11 is just crazy. It says, would you consider 68 correct answers on a 100 question multiple choice test with 4 choices each to be unusual? All right, so 68 is the passing score. You know, it's a high D. Right, so we would want to know, is that going to be unusual? It ought to be probably unusual, because you know, you're not looking at a situation that people would say, well, yeah, 100 question test, I'm just going to guess on every question, I'm totally going to pass. You know, you're probably not expecting that. So let's back it up. So mu equals NP. Sigma is equal to the square root of NPQ. Or if you like, NP times 1 minus P. It means the same thing. All right, so number of trials, N. Probability of success, 4 choices. So probability of success would be 1 out of 4. So mu would be equal to 100 times 1/4, which is 25, which ought to make sense. You know, 1 in 4 chance of getting a question right. There's 100 questions, so you probably expect to get about 25 of them right. Sigma would be equal to the square root of my previous computation, but also multiplied by Q, which is the probability of failure. And the probability of failure is 3/4. So the square root of 75 over 4. If I can get a 5 to show up. So we're talking about 4.33-ish, 4.330, right? And we want to know, is 68 going to be unusual? Well, now that I have a mean and standard deviation to work off, if I can say mu plus or minus 2 sigma, so that's going to give us 25 plus or minus 4.330 times 2, sorry. I hadn't made a mistake in a while, so I felt like it was necessary to screw something up. Oh, I lost a little flare on the 5 there. Anyway, so 25 minus 2 times 4.330. Lost my little decimal point too. So on the low bound, we got 16.34. And on the upper bound, a little duplication here, 33.66. All right, so this is the usual range. So this is what you would expect to be the case under ordinary circumstances. You guessed on every one of the questions, you can expect to get somewhere between 16-ish and 34, 33, 34 questions right. All right, so would I consider 68 questions right? Yeah. Therefore, 68 right is unusual. It's actually extremely unusual to the point of being an outlier, but that's not what the question's asking. It's saying just whether or not it's unusual. And then, you know, do with that what you will, because now, you know, as a teacher, I know that a person ought to get somewhere between 16 and 34 questions right on a test if they're guessing. So if a person got 68 questions right, well, I can probably assume they weren't guessing. I'm not going to assume they were cheating. I'm going to assume that they probably studied a little bit. Yeah, could they have studied a little bit more? Sure. But they did do some studying. Otherwise, they would have, like if they did no studying whatsoever and they just randomly guessed, which is probably what would happen if you did no studying and you weren't familiar with the concept, then you're probably looking at something, you know, in the 20 to 30 interval, right? But because that didn't happen, they got something in the high 60s. They probably did a little studying, and so it's a good way to analyze the data, but also it's a meaningful way, right? So the next page, the next problem is really just kind of more of the same. So what I'll do is I'll just kind of leave that for next time. And speaking of next time, I decided probably 5 minutes into this class that there was no way we were going to be ready to take the test on Wednesday. So, you know, I just figured I'd kind of save the surprise for the end. So I know that that's not happy news for everyone because some people are like, dang it, I was ready for the test. It's going to be next Monday. So we'll do the review this Wednesday. All right. So just so you have that, that comfort, or at least the idea of knowing that if we don't have to try to shoehorn in a review in like 20 minutes, you know, like if that wasn't the plan. Oh, they're rolling in now. I don't even have the heart to look. If it's anything negative, I don't think I can make it.
Thank you, Professor.
You're
Everybody say
unanimous.
Oh,
thank you.
it's all. Oh, it's good stuff.
Unanimous.
Oh,
Unanimous
it's all
shooting
nice
for
stuff. Oh, that's
MVP.
great.
Congratulations.
Oh, Oh, that makes me so happy. I thought it was going to be like, why didn't you tell us before? You know, I don't know. I guess I probably could have, but
It's been stressful lately with work and a lot of stuff. So thank you.
yeah, no problem.
Also, tomorrow's going to be stressful, so thank you.
Yeah, no problem. I honestly, I'm at the point right now where my eyes are barely staying open. So like daylight saving time always really kind of gets me. And between that and just like life, I'm just shot right now. So I figure
you just
everybody
did
else
this
has got to be kind of in the same boat, you know?
Oops.
So we'll worry about the review on Wednesday. I'll take you through a good review on that, on all this stuff, and then we'll go from there. I'll also go back and grab some of the things that we kind of skipped over here. So if, so at this point, I'll end it. So if you have any questions.
Is the tech assignment also going to be due on next Monday?
Sure. Yeah, we'll go for that too. But if you have it done already and you want to submit it, you're welcome to do that, because I've been trying to like stay on top of grading those things. So you don't have to wait on the tech assignment. And I know there are some people that are really behind on the discussion board. So definitely don't dilly-dally with that. You know, so you got the gift of time. So get something up on the discussion board, comment on the posts of your peers so you can get the credit for that, and also, you know, add to the conversation. But get that tech assignment in. That's, you know, sooner rather than later. All right. So with that, if you have any questions, stick around. Otherwise, have a wonderful evening, and I will see you on Wednesday when hopefully I'm.
Thank you so much.
You're welcome.
Thanks, Professor.
Thanks, Professor.
You're very welcome.
Good luck, everyone, tomorrow. It's going to be crazy out there.
Stay safe, everybody.
It is.
Board up your windows.
Stay frosty.
What's the probability of stay frosty?
Probability of the freaking apocalypse.
That would have been a fun Dean question. All right, thank
What's
you.
the probability of your windows being
Smashed in front of
smashed tomorrow? Professor, I have a question.
Sure.
With regard to the tech assignment, I was looking at something here. I had a little issue with my tech assignment. On the Google Sheets, I don't know why. Every time I retrieve it, it's like all